So we're going to continue on in Chapter 8. We just discussed extensions of Mendelian genetics, and now we're going to talk about sex determination and sex linkage. We'll cover three main topics: X-linked genes that are passed to both sons and daughters. We'll also talk about Y-linked inheritance patterns. And lastly, we'll talk about X inactivation, which takes place in females. So for this portion of the lecture, we're just going to be talking about the sex chromosomes, the X and Y chromosomes, as opposed to the autosomes, which are all the other chromosomes in the body. As you can see here, the X chromosome is significantly larger than the Y chromosome. The Y chromosome is actually the smallest chromosome in the body. However, there are several very important regions in the Y chromosome, one of which is the sex determining region, and this is what determines whether someone is male or not. So if you do not have that sex determining region, then you will be female. So as I mentioned, all humans have 22 pairs of autosomes, and they have one pair of the sex chromosomes. Women have 2 X's, and men have 1 X and 1 Y. So the sex-linked genes are those that are located on the sex chromosomes. For the most part, what we'll be talking about are X-linked inheritance traits. These are all located on the X chromosome. There are a few that are located on the Y chromosome, such as the SRY gene, which leads to the development of the testes and is in that region, that sex-determining region I mentioned earlier. So males will always inherit their X from their mother, and they're more likely to express recessive X-linked traits than females because they're only carrying one X chromosome. So if there's a mutation on one of the X chromosomes, then the males are more likely to express that recessive trait. Females are less likely to express the X-linked traits because they have 2 copies of X chromosomes. So if we're talking about someone being a carrier for an X-linked trait, that can only be a female, since if it was a male, it would have an X and a Y. If it had the mutant allele, then the male would be affected. So only heterozygotes can be simply carriers for recessive traits. Hemophilia, red-green color blindness, and muscular dystrophy, these are all examples of sex-linked traits. So let's look at color blindness first. So color blindness demonstrates a pattern of inheritance that's different than traditional Mendelian traits. For people who are colorblind, they may not see this red 8 in the center of this green circle. So they may see the number 3 or no number at all. This is known to affect somewhere between 5 to 8% of all males, but it's very rare in females. This is because, again, you have to have mutations in both of the X chromosomes that you inherit from your parents to have it as a female. So let's do a series of crosses. What I'd like to do, I'm going to set up the scenario. I'd like for you to set up the Punnett square, put the video on pause, and then try these problems out yourself. And we're going to look specifically at color blindness. So here we have a female and a male. For this first situation, the father is normal, but the mother is a carrier. So the father is carrying big C, and the mother is carrying big C and a little c. So go ahead and set up the Punnett square, and put the video on pause, and see if you can predict what the offspring will look like, whether they're male or female, and whether they have the color blindness allele or not. So here we're showing plus as a wild type, and little c is written as the C. So what you can see in that first quadrant, we have a female who is wild type, shown as plus plus. If you go to the bottom left quadrant, what you can see is we also have a female who happens to be a carrier for the colorblind allele. She doesn't actually have color blindness, but she's a carrier. If you go to the top right quadrant, we have a male, because it's XY, and since he has the wild type allele, as exemplified by the plus, he is not colorblind. However, the fourth child here is a male who is colorblind because he has that mutant allele on his X chromosome. So now let's try setting up a Punnett square where the father is colorblind but the mother is normal. So you should see something like this, where all the girls are carriers since they are getting that mutant allele from their father for the colorblind gene. They are carriers for colorblindness now, although they themselves are not colorblind. However, all the males are not colorblind in this family because they got their wild type colorblind alleles from their mom. Okay, let's set up another scenario. We have a colorblind father and a mother who is a carrier. So in this situation, what we have is both a daughter and a son who are colorblind, and we have a daughter and a son who are both wild type. However, the daughter is a carrier for the colorblind allele. Why are X-linked traits never transmitted from father to son? Simply because the father is passing on to his son the Y chromosome. So here you can see how hemophilia has affected the royal family over time, and starting all the way back with Queen Victoria, which indicates that probably Princess Victoria, her mother, had a mutation in her X chromosome that then got passed on to Queen Victoria at some point. And what you can see is that different offspring were clearly affected or then were carriers of the disease gene. We know that there are several genes on the X chromosome that are necessary for both males and females. We also know that males are only getting one X chromosome, so it must be the case that having just a single X chromosome provides you with adequate concentrations of the proteins that are ultimately synthesized as a result of gene expression on that chromosome. So what would happen if in females we express twice as many genes and thus twice as much protein? And that would actually cause a huge problem. So what females do is we actually inactivate one of our X chromosomes. And this ensures that all females receive just one dose of the proteins on the X chromosome. Inactivation of the X chromosome is irreversible, and this happens during cell division. And it's the result of a specific type of RNA that wraps around the X chromosome. So X inactivation is exemplified nicely in cats from their determination of coat color. So the coat color gene is on the X chromosome, and the dominant form is the allele for black coat color, or big B. And if you inherit little b if you're female, or just little b along with the Y chromosome for males, then your coat color will be orange. So if we are to cross an orange male with a black female, if this were to behave in a traditional Mendelian manner, we would expect all the offspring to be black since it's dominant. However, what we see is actually a calico cat. We have the black allele inherited from mom and the allele for the orange fur inherited from dad. What we see is this very spotted pattern. And why? Well, somewhere around the 16th cell division, so here we have an egg that gets fertilized by sperm, and then it will undergo several rounds of cell division. So once it gets to that 16th cell stage, that's when we have X inactivation. And it's random which X is going to get inactivated. So sometimes it's going to be the X chromosome that's carrying the allele for the orange fur, and sometimes it'll be the X chromosome that's carrying the allele for the black fur. And that's how we get these calico type of cats that have both orange and black fur. So that concludes our discussion of sex determination and sex linkage. Actually, I'm not going to do a short video lecture on pedigree analysis because it's covered very well in your text and it's somewhat self-explanatory. So go ahead and read that section on your own, and we'll pick back up talking about DNA fingerprinting.